All right, Cogging Torque. Every one of you has felt this phenomenon before you ever took a machines course. If you've ever picked up a small stepper motor or a hard drive motor and spun the shaft with your fingers, you've felt little detunts, pulses, almost like a ratchet. That sensation is cogging torque, and by the end of this slide, you'll understand exactly why it happens, down to the field equations. Let's start with the formal definition. Cogging torque is the torque produced purely by the interaction between the rotor's permanent magnets and the stator's ferromagnetic teeth. And notice the key phrase here, independent of any winding current. There are no amps flowing. This is not a motor torque. In the electromechanical energy conversion sense we'll study later with the Lorentz force and back EMF. This is a reluctance phenomenon. The rotor is simply trying to minimize the magnetic energy stored in the system. And it does that by pulling the magnets toward the position of least reluctance, that is, toward the nearest tooth, where there's the most iron for the flux to travel through. Now, why does this actually produce a torque? Recall the general co-energy expression for torque. Torque is the negative rate of change of the field's reluctance energy with respect to rotor position at constant flux. In simple terms, cogging torque is proportional to minus the flux squared times the rate of change of reluctance with respect to angle. Two things to internalize from this relationship. First, reluctance here is the total magnetic resistance the magnet's flux sees as it crosses the air gap into the stator iron. As the rotor rotates, that flux path length is not constant. Right under a tooth, the path is short, just the air gap length. But right under a slot opening, the flux has to travel further to reach the iron, so the effective reluctance is higher. That variation in reluctance with angle is the entire root cause of cogging torque. If you had a stator with absolutely no slots, a smooth, slotless bore, that variation would be zero everywhere, and cogging torque would vanish completely. Every design trick we use to reduce cogging torque is really just an attempt to flatten that reluctance curve. Second, notice the flux term is squared. That means cogging torque doesn't care whether the flux is pointing north or south through that piece of iron. A north pole and a south pole, passing the same tooth, produce the same sign of cogging pulse. That's why the wave form at the bottom of this slide shows a clean periodic ripple rather than something that flips sine pole by pole. And that brings us back to the everyday illustration. When you spin that unpowered motor shaft, you're feeling exactly this. The magnets snapping from one equilibrium, the nearest tooth, to the next. Engineers actually use this qualitative shaft spin test all the time. But I'll warn you now, and we'll come back to this on the next slide. It's a deceptive test because in a running motor, current-related torque ripple is usually larger than cogging torque and can completely mask it. Now let's ground this in a real machine. This is a surface permanent magnet motor cross-section, copper windings in the stator slots, laminated steel teeth in blue, curved surface-mounted magnets in gold and navy for north and south. Press play or drag the rotor in the interactive version and watch the torque trace ripple every time a magnet edge sweeps past a slot opening. That's the reluctance variation made visible. Cogging torque shows up anywhere you have a slotted stator with a PM rotor. BLDC motors, PMSMS, steppers, PM generators. It's concentrated right at the air gap, where the magnet meets the slot openings. And it has nothing to do with the winding. Disconnect every phase lead and it's still there. Is it good or bad? Depends on the application. In a stepper motor, it's often wanted. That's détente torque, holding the rotor in place with no power applied. In a BLDC or PMSM drive, it's usually unwanted. It causes torque ripple, vibration, and noise. Though in practice, back EMF/current mismatch often causes more ripple than cogging does, so don't overblame it. 3 ways to reduce it, all aimed at flattening the reluctance variation. Narrow the slot opening or improve the tooth shoe shape. Though too narrow hurts winding insertion and raises leakage inductance. Use a fractional slot combination instead of an integer slot one. So pole-to-pole cogging pulses partially cancel instead of adding up. Or skew the slots or magnets along the shaft, spreading the transition out so net torque stays flatter, at the cost of a bit of average torque and back EMF. Bottom line, cogging torque is a reluctance-driven, current-independent effect. Whether you want it or fight it depends on the application. And every fix is just a different way to smooth out that same reluctance curve. Now let's ground this in a real machine.